we present our work titled What is Learned in Deep Uncalibrated Photometric Stereo. Uncalibrated photometric stereo is a technique for estimating the surface normal of an object, given images captured under varying light directions. Following the conventional assumptions, we assume a distant point light source, and an orthographic projection. The image formation model for a surface point can be written like this. M is the measurement, E is the light intensity, ρ is a BRDF determined by the surface normal, N, and light direction, L. Max accounts for attached shadow. For each pixel, given an image, we can write down one equation. Given F images, we can write down F equations. To solve for the surface normals, previous methods often assume the light directions and intensities to be known, or a Lambertian reflectance model, where the BRDF degenerates to a scalar. In this work, we consider the more challenging problem of uncalibrated photometric stereo for non-Lambertian surface. Most of the existing methods are based on the matrix decomposition technique. They first apply SVD to decompose the measurement matrix to a pseudo-surface matrix and a pseudo-lighting matrix. However, there is a 3x3 linear ambiguity. By applying surface integrability constraint, the ambiguity can be reduced to a 3 parameters GBR ambiguity. This GBR ambiguity indicates that there are infinitely many combinations of light direction, light intensity, albedo, and normal that produce the same appearance. It is worth noting that, after GBR transformation, the albedo will become spatially varying according to the value of surface normal. Existing methods rely on addition clues to resolve the GBR ambiguity. For example, albedo distribution, light intensity, etc. PF14, based on the clue of Lambertian diffuse reflectance maxima, is the most robust non-learning method so far. Recently, Chen et al. Introduce a lighting calibration network, called LCNet, to estimate lightings from images. LCNet first extracts a local feature for each input image, and then fuses them to be the global feature. Then each local feature is concatenated with the global feature, for estimating the corresponding light direction and intensity. Given the estimated lightings, state-of-the-art calibrated methods can be applied to estimate the surface normals. LCNet achieves promising results in estimated directional lightings on multiple real datasets. However, what specifically inside the network contributes to its success remains a mystery. In this work, we first analyze what has been learned by LCNet for lighting estimation. We test LCNet and PF14 on 3 surfaces differed by GBR transformations. The first row is a sphere with uniform albedo. As these 3 combinations of normal, albedo, and lighting produce the same set of images, the outputs of LCNet and PF14 for these 3 shapes are the same. Note that the estimated lightings are most close to that for uniform albedo, indicating that LCNet learned from the training data that GBR transformed surfaces are unlikely. We then test LCNet and PF14 on different BRDFs. Compared with the non-learning method, LCNet performs particularly well for non-Lambertian surface, indicating that specularity is helpful for lighting estimation. To understand what has been learned by LCNet for lighting estimation, we visualize its learned local and global features. We find that the sum of the learned features are closely related to attached shadows, shadings, and specular highlights. To further verify our observations, we first computed the attached shadows, specular component, and shading using ground truth normal and light directions. We then used these as proxy input for training and testing LCNet. We found that the models trained with proxy input achieve comparable, or even better results than that trained with images. Here we visualize all the local features and global features extracted from a sphere scene. This is the feature visualization for a pot with complicated geometry. Similarly, we can observe that some of the learned features are closely related to attached shadows, shadings, and specular highlights. We now introduce our motivation for the proposed guided calibration network. We know that LCNet tries to extract information like shading, shadow, and specular highlight for each image. However, these information are determined by the surface normal and light directions. It is therefore suboptimal to extract them for each image independently. We propose to first estimate surface normal as an inter-image guidance for feature extraction. We first introduce a lightweight lighting estimation network, and a normal estimation network to predict coarse lightings and normals. We then use the estimated normal and computed shading to be the additional input, to guide the feature extraction of the second lighting estimation network. Following LCNet, we trained our model with the synthetic dataset. We first trained the subnetworks one by one, and then fine-tuned the whole network in an end-to-end manner. Let's look at some experimental results. Here are results on a synthetic dragon scene. Our approach consistently outperforms LCNet on 100 MIRL BRDFs. Here are results on 2 real objects. Our approach achieves the lowest error in light direction and intensity estimation. Given our more accurate estimated lightings, existing calibrated method can achieve better results for surface normal estimation. Thank you for your attention.